We're going to look a little bit more at some examples of ideal systems where we apply conservation of energy. Specifically, all of these problems will involve either the spring force or force of gravity, or some combination of both. When you think of a spring hung vertically, and we did this demo in class the other day and let it bounce up and down, and I sort of did a couple of things that you might call a cheat. I made it so that we were measuring zero force when the mass was hanging on it at equilibrium, because that would give us a simpler idea of the spring. But there's a lot that can be done with a spring, and so we want to kind of look at that. So if you imagine a 1 kilogram block is placed on a spring and compresses it 10 centimeters. Now, because it's on top of it and not just a horizontal compression, it didn't just change the compression of the spring or the delta X, it also changed its height, right? Then it gets pushed down an additional 20 centimeters. And how high does it go when it's released? So there's a lot of things here that we have to think about. So the maximum height that it goes after it's released is really what we're looking at. How far from its lowest point would be a way to do it. You could also do this from some other reference point, but there's no real reason to do that. First, we need to find the spring constant. And in order to do that, we can just use the modification of Hooke's law that says the applied force that compresses the spring is equal to Kx. In this case, we placed a block of 1 kilogram, so that's a 10 Newton block on a spring, and it compressed 10 centimeters. So that gives us 100 newtons per meter. Once we know that, we can go on for the rest of the problem. But I want to make a point here. If you wanted to try and find the spring constant by using conservation of energy, mgh equals 1/2 kx squared, this is incorrect. And it's not immediately obvious, I think, why it's incorrect. But the reason it's incorrect is in order to compress it, we're basically letting it be at equilibrium. And in order to do that, if you just drop that block on it, it would bounce up and down for a while and eventually come to equilibrium because of air resistance and thermal dissipation in the spring and some friction and that kind of stuff. And that is work done by something. And that's not in this equation. So that's why this equation doesn't work. So it's very important to remember that when we set something in equilibrium, we apply a force, and we see that something is compressed in a spring, that's a Hooke's law situation. When we let something go and be released and let it move freely without putting something like a hand in there to mitigate it, then we're talking about a conservation of mechanical energy problem. So now when we're talking about releasing it and letting it spring upward, that's what we're looking for. So we know we start with spring potential energy, and we're going to call the height that it's at the beginning 0. So we can say there's no gravitational potential energy. And our interest is in the point where it reaches its highest point, which for vertically launched, free fall problem will be when the velocity is 0. This now is 1/2 kx squared equals mgh. And this is why another example of why this is not an okay equation for the previous situation. The previous situation was not drop a block and see how far down it gets compressed before it jumps back up. It was at an equilibrium situation. So in this case, we have height 0 at the starting point, height final up there. Kx squared divided by 2mg ends up being our relationship when we get about 45 centimeters. So another question you might ask is, when is it going the fastest? And this is not the most obvious answer necessarily, because it's certainly at rest at the top, but it's also at rest at the bottom. So it speeds up and then it slows down, right? The spring is accelerating it up, but then at some point, the force of gravity takes over and starts slowing it down. And so we need to figure out where it has its maximum velocity. There's a bunch of possibilities. Is it at the beginning? Is it at the end? Is it when you reach that point where it was at rest at equilibrium before, or when you reach the unstretched length of the spring? Where is it that this happens? Well, it turns out that it's at point C, where it was at equilibrium before. And the reason for this is when it's at that point, right, is that the net force when it's at B is the force of gravity, right? And as soon as the spring releases it, right, goes completely unstretched, then that's the force of gravity. But if, as we're going from C to B, the force of gravity is getting bigger. Well, it's staying the same, but the spring force is decreasing, and we're getting a smaller upward acceleration. And so, or in some cases, you could say, or I'm sorry, you would say a downward acceleration because the force of gravity is bigger than the spring force. Only at C is the net force zero. And if the net force is zero at that point, the spring force and the force of gravity, then the acceleration is zero. Before that, when it was compressed more, the spring force was bigger. And once it's above that point, the spring force is smaller. So we will get an acceleration either up or down. So this is the maximum velocity, right, at equilibrium. And this ends up being important. We'll talk more about this when we get into simple harmonic oscillators, mass spring systems, that the fastest the mass spring system goes is when the forces are balanced at equilibrium. All right. From D to C, spring force is bigger, so we have positive acceleration. And from C to B, we have negative acceleration. All right. What if the mass actually sticks to the spring? So what if we attach it? Well, then we get a slightly different scenario because instead of, just being launched upward, the spring then stretches out. And of course, as the spring stretches out, we store energy again, right? So now the conservation of energy equation changes to have both gravitational and spring potential at the end. So we have a slightly larger equation, slightly more complicated. And the height we go up is the initial compression plus the final stretch length added together, right? So we now have an equation in terms of our initial and our final x. We're going to have to do a little bit of work to kind of rearrange that. We've got an x final and an x final squared. So we're going to need to use a quadratic to solve that. And we end up with possibilities of positive 10.1 meter or negative 30. And the only one that makes sense is the positive 1. And so we add that to our 30 centimeters, and our height is 40 centimeters above the lowest point. The negative solution is back when it was at height 0, which is the other option, right? That's when it's stopped as well. Either the spring hasn't been released yet, or it comes all the way back to it. So another way to look at this is if the equilibrium position is the height, then it goes up 20 centimeters or down 20 centimeters, and it'll oscillate between those 2 points. The other type of problem that we might want to look at is a circular motion and energy conservation problem. If you remember the turning point lab, we had to combine those two things together a little bit already. But here what you have is you're releasing something down a track and then it goes up around a circle. And we want to know how high do I have to release this thing from so that it just gets around the track. Now you might initially think, oh, just the height of the circle. But if it does that, then at the top of the circle, it will be at rest and it will fall straight down. We need it to get around that circle. So we need to use what we know about circular motion, which is that the minimum speed to get around comes when the normal force goes to 0. And so the force of gravity is our centripetal force. We get V min as the square root of RG, something we've already solved from circular motion. And then we can say, well, we start with no kinetic and no spring. And at the end, we have both kinetic because it's getting around the circle at the top, and we have gravitational potential energy. So we can take what we know for H minimum and find it using that. All right, so there's a couple of example problems for ideal systems.